Okay guys, welcome back. Today is day 2 of making a VR game. Today we're going to get into the build settings, the player settings. We're going to look at the project settings quality and get this set up. And we're also going to get into the project settings graphics and get all this set up. So stay tuned. Let's get right into it. Yesterday we got Unity installed and everything that we need. And so today I've actually switched computers back to my regular development machine. So on this one I have Unity 5.4.2 and Unity 5.5. Yesterday we installed Unity 5.5 and that's what I want to use for this project. So when I open up Unity 5.5, I can see which projects here are my Unity 5.5 projects and which ones are my Unity 5.4.2 projects. So I don't get them confused and open the wrong one. But we're going to make a new project like I did yesterday, and we'll call it VR tutorial game. And this is just duplicating a little bit of the work that we did yesterday. So we got an empty project, and I want to bring in the Google VR SDK version 1.03. So this is the Google VR SDK for Unity GitHub page. And like yesterday we clicked on this, but like Kent said in the comments, you can also go to this releases button. So I'm going to click on the releases. And here's 1.03, and that zip is what we've downloaded already, and inside of that zip is the Google VR for Unity package, of course. So we're using Google VR 1.03 just like yesterday. So I'm going to deselect the iOS and 32-bit plugins, and then it's going to want me to first of all update the scripts. So I'm going to click that, and then the next thing it's going to do is it's going to want me to import the additional package here. And I got to click into Unity to get that window to show up and import that. Okay, so we're just getting caught up like we were yesterday. We had opened up the demo scene and the headset demo. So here we are. And we essentially had switched the platform over to Android and add this scene to the build, and then we build and run. So that's where we're at right now. Now, today for day 2, I want to go through all of the build settings, which is the player settings right here for Android that we're going to be going through, and I also want to get into the project settings quality, and we're going to get into the project settings. And so once we set all these settings up, we are ready to build the project again. And at the end of the day, we're going to have the same exact project that we did yesterday, but all of the settings are going to be set up. Now, it's important to do this at the beginning of your project because these graphic settings have to do with shaders and materials and textures and your 3D models and how big they are, and if you combine them with other 3D models that are in your game. And so these settings unfortunately aren't that exciting, but it's important to learn them because how we design the game is going to be dependent on how we set these settings up. So in other words, if I go design a game without worrying about all these settings, and then I got to go back and configure the player settings, the graphic settings, and the quality settings, then we're going to have to go through and completely redesign all the work that we've already done. So this should get done first, and we should get all these concepts down now so that as we design the game, it gets designed correctly so we don't have to redesign it when we get done. Okay, so first of all, let's go through the build settings. Now, we've already switched over to Android, and we need to get the texture compression set up so that as we import textures, the proper texture compression is there. There's essentially two options. You could use ETC2 or ATSC. And so I don't know definitively which one is going to be better. It probably depends on your game, but based on my research, I believe that ATSC texture compression is going to be better. For one, here on Oculus's site for Unity mobile performance, be sure to use texture compression, and we recommend using ATSC texture compression as a global setting. And so in this forum post on Unity's forums, he's basically saying that using ETC2 kept crashing on large textures, 4K, and the ATC build took approximately 13 hours to build. So I've never seen anything like the 13-hour texture compression. Sometimes it's taken quite a while to do the ATC texture compression when you import the image, but I've never seen anything like 13 hours. So if ETC is crashing, I could see a reason to perhaps use the ATSC. And just so I learn for myself, ASTC, so I don't get the mixed up again, is Adaptive Scalable Texture Compression. So ASTC, now we know what it is. We're going to be using ASTC texture compression in this project. Let's get into the player settings. Now I'm going to start at the very top under resolution and presentation. And a good place to follow along with this is on the Unity's documentation for the Android player settings. And it's going to go down and we can follow along and read about everything that we're doing. So we're going to jump right back into Unity and go through this. I'm going to close this build window for now since everything is configured here. And first of all, auto rotation doesn't work. We need to go landscape left for Google VR. Use 32-bit display buffer. You don't want to use 32-bit display buffer. You want to disable this, which is going to use the 16-bit display buffer. So again, back to the Oculus mobile page here, frame buffer format, 16-bit depth buffer. And if we look at the Unity forums here, we'll see that 32-bit display buffer utilizes more bandwidth, which is probably the most expensive thing for mobile VR in terms of power and heat. So it's recommended that you use 16-bit if you can get away with it, which we're definitely going to get away with it. So same with the depth buffers, but that's a Daydream only setting. So we're going to disable the 32-bit display buffer. The next thing we're going to do is check this, which disables the depth and stencil buffer. Here on the Oculus site, check the disabled depth and stencil checkbox. So unless you specifically need to use the depth or stencil buffer with one of your shaders that you're using, you should disable it. And the reason why is because there are extra buffers, and for example, the depth buffer is a buffer which tracks the depth of every pixel on the screen. So this might you might need a shader that needs to use this, like an outline shader or something. And if that's the case, enable it. But otherwise, disable it, because not tracking, when it comes to mobile VR, per pixel operations get really expensive, and so we're going to get into that with lighting later. But essentially, the rule of thumb here is to disable the depth and stencil buffer unless you get into a situation where you're using a shader that needs to use that. Now we're going to not show a loading indicator. The icon we can set up later. These names up here are we want to set those up when we publish, but it's not important at the moment. Splash image, we're just going to we'll set that up later when we're getting ready to publish. And so we're at the main settings screen here, the other settings. Now there's color space in Unity 5.5, and we can select gamma or linear. Now, before I get into that, I want to jump ahead to the Auto Graphics API. I'm going to uncheck Auto Graphics API. And what that is doing here is let us check between OpenGL 2 or OpenGL ES 3 and which one we're going to support depending on the device that's being used. And so if we look at the devices that OpenGL are using and the OpenGL ES 3 are using, we'll see that OpenGL ES 3 is used by basically the low-end mobile VR devices. So if you have a device that's, you know, Raspberry Pi runs OpenGL ES 2.0. So I don't believe if you're running OpenGL ES 2.0 device, you should be running mobile VR. And so we're just going to use OpenGL ES 3.0. And so like yesterday, if we go to the Android dashboards and we look at what devices out in the world are being used, this represents a really small piece of devices that are out there. 4.4 and above is going to be the majority. In fact, 5.0 and above is more than 50% of the devices out there. So it's fine to make something that supports 4.4 or 5.0 or above, which kind of ties into which GPU it has. If it has the Snapdragon. So these are, you know, pretty low-end devices. So I'm going to say we're only going to support OpenGL ES 3.0 devices. So I'm going to take away OpenGL ES 2.0 and turn off Auto Graphics API. And so that's going to lead into the color space decision because we can either pick gamma or linear here. Now, if you want to read more about gamma or linear, it has to do with the color space and how the colors are going to be determined. And so not all devices support linear color space. So here's a list of the supported platforms. And that's Xbox One, PlayStation 4, Android, and iOS. And so on Android, linear rendering requires at least OpenGL ES 3.0 graphics API on Android 4.3. And so that's fine with me because we don't need to support 4.3. We're going to be running 4.4. We've already determined that OpenGL ES 3.0 devices is kind of like the bottom line of devices that should be running mobile VR. And so on Android, we can definitely run linear color space. And I haven't done extensive testing on performance here with linear color space, and I need to, but it looks like it should be okay. And so here we got gamma and linear color sampling occur at the shader level. So I don't think there's any specific benefit to a deferred pipeline. And so it gets down to kind of like I believe Unity says here, an artistic decision on what you think looks best. So it's kind of up to you. Do some testing, but I'm going to go with linear because that's kind of a new option. Well, it's a very new option, and it only works on basically our bottom line platform, Android 4.4 with OpenGL ES 3.0. So it should be fine. Now I'm not going to require OpenGL ES 3.1 or 3.1 plus AEP because I want devices like the S4 or whatever to be able to run this. Now we're going to turn multi-threaded rendering on. Multi-thread rendering is absolutely recommended. This will free up time on the CPU main thread, which is the bottleneck for most mobile games. So we are going to enable multi-threaded rendering. Now static batching and dynamic batching. This gets pretty complicated. So this batching has to do with draw call batching. And so specifically not exactly draw calls, but the state change that's done between the draw calls such as switching to a different material. And so what this means is if you have two objects in your game and one has texture A with material A on it and the other one has texture B with material B on it, then those two objects take two draw calls to draw, because it has to draw each object in every single frame, and it has to switch the state in between so that it could switch to that different material. And so the best thing to do is to manually batch our scene and our models and our textures and our materials, so that there's a very small amount of textures, a very small amount of shaders being used, and very small amount of materials being used, and again a small amount of models. But we also want to turn models off when they're not being seen, so we need to break models down to some point. And so basically you want to stay well under, at least stay under 50 draw calls here in mobile VR. And that is set pass calls. If I were to look at the stats here, we're going to see the set pass calls here. And right now it says 4. If I play the game, that should go up quite a bit here. And so yeah, here we go. We're up to 18. So we need to keep this number of draw calls under 50. And so as we add models with different textures and materials, that number is going to start going up and up and up. And so we need to manage that. To help bring those numbers down, there's dynamic batching and static batching. Now, neither one of these is a very good option for mobile VR, because we're going to look at that right now. But basically, it would be best to turn both of these off and batch everything ourselves through really good modeling, really good texture management, atlasing, texture atlasing, and material management. So let's take a look at this. Dynamic batching is for objects that are moving in the scene and they don't have the static checkbox on them. And the static checkbox, of course, is right here. And so if an object is going to move in the scene, it's not static, and it shouldn't have this. But if it's just going to be static, we're going to set that, and that gets into static batching. But first, let's deal with dynamic batching, objects that are moving in the scene. So for small enough meshes, this transforms the vertices onto the CPU and groups many similar vertices together and draws them all in one draw call. And so the limitations on this are pretty strict, and I'm going to recommend to turn off dynamic batching. So we need to get back to the build settings. I'm going to turn off dynamic batching, and let's look at why. Because dynamic batching has a certain overhead per vertex. So it only applies to meshes containing fewer than 900 vertices total. And so this could be vertices, for example, if you have a vertice attribute like color, so you vertex colored your model, that counts as a vertice attribute. So you can see if your shader has a vertex position, which we have to have the vertex positions to make a mesh, and then it has a normal and a single UV, then you can batch up to 300 vertices. So that means that you're going to have to keep this isn't going to work for models, for example, like characters, because unless your character has a really low vertex count, and here it has a UV, we're not going to use normal map, but we got a vertex position, a UV map on the guy. So we're immediately down to 450 vertices to consider him in dynamic batching, which is a really low poly character. And so game objects are not batched if they contain mirroring of the transform. So if you scale an object with a negative, it's not going to batch. using different material causes game objects not to batch together. So if they got a different material, they're not going to dynamic batch. And then it talks about game object with light maps, but pretty much we're dealing with dynamic objects that are moving, and so it's really rare to have a moving object that needs to get a light map baked onto it, because you're baking the shadows, and as it moves, it's not moving with the light. So it's pretty much, if a game object has a light map, it's set to static anyways. And so multi-pass shaders break batching. And this has to do with per pixel lighting, and we're not using per pixel lighting because we're going to use legacy vertex lit rendering path. So going through all that, I really don't see an advantage to using dynamic batching. A situation where you may want to use dynamic batching is if you have, 10 or more objects in the scene that have very few vertices and vertex attributes. So let's say like a cube. Let's say you want to put 50 moving cubes on the screen. That's an option where you might want to use dynamic batching. So I don't know what game we're going to end up making, but if we end up with 50 moving cubes or something of that nature, we may turn on dynamic batching. Let's look at static batching. Static batching allows the engine to reduce the draw calls for geometry of any size, provided that it shares the same material and it doesn't move. So this is more efficient than dynamic batching because, but it does use more memory. Using static batching requires additional memory for storing the combined geometry. So if several game objects share the same geometry before batching, then a copy of the geometry for each game object in the... So long story short, when it makes a copy, it still has to keep the original model, plus it's making this generated model that's a combination of two different models, and that 3D model has to be saved into memory. So it increases the memory. Now, it would be better to simply use, there's assets on the asset store to do this, or you could use a 3D modeling program to combine meshes ourselves, so that Unity doesn't have to do that and then save the duplicated meshes into memory. So static batching is kind of a good thing for just throwing a bunch of stuff into the scene that's static, and then have Unity batch that together. But for mobile VR, we're already under a ton of constraints. When we're prototyping, maybe it's a good idea to keep static batching on so that we can make prototypes. But in the end, when we finally publish this thing, we really should group those models together that are static and that need to be batched together. We really should group those together as the mesh itself needs to be group made. So for example, if we have a room with a chair and a table and a computer on it, and they're static and they just sit there, and we drag the table in from the 3D model, we drag the computer in, we drag the chair in, we set everything up, and then static batching is going to batch that into a new model and then have to save that into memory. So it's going to be better for us to go, when we're all done with our game and those objects we know we're not going to move them, let's combine the chair, the table, and the computer into one mesh, and one material, of course, and then we can turn off static batching and reduce the memory. So the long story short here is static batching is a good thing and dynamic batching is a good thing, but we really want to have good enough control on mobile VR that we're not using the extra memory, we'll take the time to group that model into one model. There's assets on the asset store that make that really fast and easy, and also it's easy to do that with the 3D modeling program. So we're turning off static batching and we're turning off dynamic batching. Now we might come back and turn these on depending on what we end up building into the game, but as a rule of thumb, we want to have those off and manually control our models, our materials, our shaders, and our set path skulls. So the next option here is GPU skinning. And GPU skinning is a relatively new feature that allows the GPU to do the skinned mesh render instead of the CPU, which normally happens. And so potentially it could help out and help increase performance. But looking into it, there's GPU skinning drops performance severely on some devices. We got, and this one says it's fixed, but the GPU with OpenGL 3, which we're using, GPU skinning doesn't work as expected and draws the meshes wrongly. And so GPU skinning could be a good thing because we're using GLS 3, but I haven't tested with it enough. It's pretty new, and so just looking on it, it looks like it's it could cause performance issue on some devices, and so I'm going to leave that off. Now, graphics jobs is an experimental, and I've had bad luck with this, so I don't suggest using it. Here, graphic jobs case by case. Experiment with them and see if it helps. And I'm not sure it's going to be a huge benefit on mobile. I've seen, I've had projects not work at all by using this, and so it says experimental. We're going to leave that off. Virtual reality supported. We're not going to use this because we're building for Google VR. But when we build to the Gear VR build, we are going to have to toggle this on for that Gear VR build. Now here is the bundle identifier. This is the Android bundle identifier. We're going to need to name this correctly once we've decided what the name of the game is. So for now, I'm going to do I'll call it VR tutorial game. And you need to at least change this. Unity won't let you build an APK without changing that to something. Now this is version control. We will talk about that later in the series when we're publishing to Google Play. And we've already looked into this, and we've decided that Android 4.4 API level 19 is pretty much as low as we want to support. And that covers a lot of devices. So about 75% of the devices out there. Now scripting backend is we can use Unity's Mono or IL2 CPP, and IL2 CPP I won't get into it too much, but it actually could be a good, it's supposed to increase performance. I have seen performance increases by using IL2 CP. But it could be cause problems because it has been an experimental feature for Android, and I haven't had any problems with it though. But it does require you to install the Android NDK, and there are specific versions of Android NDK for each version of Unity. So I would need to see exactly what version of Android NDK I need to get for Unity 5.5.0. And so when I publish the game, when I get all done with it, I may switch over to this. But for a rule of thumb and to make sure it's just going to work on all devices out there, Mono is kind of the safe route to go. And then mute other audio sources is an Android option, of course, to mute other audio sources when this app is running. So if the user is listening to music on their device, you may want to mute that when the VR game starts. I don't want to use this. I'll let the user pause their own music if they want to, and that way they could get if some app gives them a beep or something, or just making a noise that they want to hear, they could still hear it. So we'll let the user decide what they want, what they want to do with their phone. The disable hardware statistics, I'm going to check that because that sends in the hardware statistics to Unity. So it's good for that to collect data, but for the best, just if it's going to skip some step and go faster, that's fine with me. Now the device filter, this lets you decide what CPU, what architectures you're gonna compile for. And ARM 7+86 is okay, but that's going to be a bigger APK file size because you're supporting 32-bit devices. Now, I don't know any 32-bit devices well, I do. There is an Intel phone with a 32-bit or with an x86 processor in it, and so. But anyways, all the Samsung phones, all these devices that are running mobile VR, they have ARM processors in them, all of them. So I'm going to select ARM processor only because that's going to reduce the size of the APK because it's not compiling unnecessary architectures that will never be used. And so we'll prefer external on the install location. This one, we just want auto because we don't want to require internet access. Write permission internal. It's not compatible with the Android TV, but it is an Android game, and it works with it works with the controller. Scripting defined symbols is for custom platform compilation, and so if you want to look more into that, go to this page and you can read about the custom the platform dependent compilation, and this is for custom. This field right here is for custom defines. Now to make it's really a hassle to deal with that stuff, so I actually have an asset that's never been purchased because I guess nobody gets into using this stuff, but I ended up wanting. I was like, man, I need a custom define manager so that when I'm building for Google VR, Gear VR, and these other builds, I can write my code to deal with that. And so that's what this asset's for. But you can kind of deal with it yourself by using this field. Now we got the .NET subset, which is okay. I don't need the full .NET 2.0. That's going to reduce my APK size. Pre-bake collision meshes. So this is going to bake the collision data into the mesh one at a time. So by default, Unity computes a physics mesh representation at load time. So we do this on the load thread, so it does not affect the frame rate when using load level async, which is cool because I use that. However, computing PhysX mesh takes time, so there's an option to bake them at build time. This increases the distribution size, but decreases load time. And so, to wrap all that up, when you load the app up, it's going to compute the PhysX meshes, and not do it when it loads scenes because that way it doesn't take a hit. It doesn't do that when you use low level async. And so it's going to increase the load time of the app, but it decreases the APK size. So I like the idea of, I don't want a bigger APK. So when I'm all done with the game, I might toggle this and watch the load time of the game versus the size of the APK and see if it makes a difference. But I like the idea of pre-baking the collision mesh so that there's a faster load time on the phone, because faster is better. So preload shaders is going to fall into the same exact category there. Anything we can do to make the game run faster is going to help. So this is actually going to increase the load time when I start the game, but the shaders will stay loaded, and they'll be preloaded, so they don't have to be loaded at runtime. But again, I'm going to be using asynchronous scene loading, so anything I can do to increase the scene load time is going to help. Then I could set preload assets. So if I had big assets that I wanted to preload, I could put into here so that they are already loaded, and it doesn't have to do that when it loads the scene. Now I could set a stripping level to try to strip code that's not being used, but I'm not going to worry about that. It's going to be a minor reduction to the APK size, if anything. So we got the enable internal profiler, and that enable this if you want to get feedback from your device while testing your projects. So ADB logcat prints logs from the device to the console. So this is a handy thing, but unless I get to a spot where I actually need to be testing at that level, then I'm just going to leave this off. So vertex compression, I'm going to leave that at the default values. And then there's also the option to optimize mesh data, which removes any data from the meshes that's not required by the material applied to them. So this kind of goes back to the static batching stuff. I think we should optimize our mesh data at the mesh level where we're editing it in our 3D modeling program, or with a tool like ProBuilder. So optimize mesh data, I'm not going to worry about that, and I'm going to say let's take optimization into our own hands when it comes to the meshes and the draw calls. Then we just get into some logging stuff and the publishing settings, which we're going to do the publishing settings later for the key store and all that. We need that for publishing to Google Play, but that's going to come at the end of the project when we're publishing it to Google Play. So the next thing we need to look at is the project settings, and we're going to go through the quality first. Now the quality settings right now is set to fantastic, and we don't want to allow that for Android. We're going to go right to simple, and I'm going to turn off even fastest and fast, and we're just going to manually set everything in one profile, and that's the way it's going to work for all devices. Okay, so pixel light count, this is the maximum number of pixel lights when forward rendering is used, but because per pixel lighting is really expensive on mobile VR, we're using Vertex Lit, the legacy Vertex Lit rendering path. So we don't need to worry about that. Now texture quality is, we'd want full resolution. So we're not going to use anisotropic filtering. Anti-aliasing, we're going to set to 2. And now we got a big problem because we're using Google VR. And let's go fix this, because this isn't going to work. Let me show you why. If we go to we need to open up a script called Base VR Device. So I'm going to double click this and open it up with Visual Studio. And in Base VR Device, I'm going to do Control F for render texture. Okay, so here we are on line 56. And so the anisotropic is already set to 0, so that's why I've set that to 0. But here the anti-aliasing of the render texture, and the reason why we're doing this is because Google VR is doing distortion correction. And so it's not just rendering a flat image. It's actually rendering to a mesh that is distorted, so that it on-distorts what happens when you view through the lens. So when you view through one of the lenses, the image gets bent because of this circular lens. And so to on-bend that, what Unity's doing is, or what Google VR is doing, is they're rendering to a mesh that's curved, that on-bends the bends that happen when you look through the lens. So that's called distortion correction, and it's rendering the camera's image for the right and the left eye to a render texture that's being put onto a mesh. Now, Unity allows you to set a render texture's anti-aliasing. So here we see the render texture anti-aliasing, and we can be set to 1, 2, 4, or 8. And so in order to get anti-aliasing to work on Google Cardboard, you need to edit this baseVRDevice.cs file because it's doing something really, I don't know why, but they're limiting the, so it's saying mathf.max. And mathf.max returns the largest of 2 or more values. And so right now I've set my quality settings.anti-aliasing, which corresponds to that setting that we just set, which is quality settings.anti-aliasing. I've set it to 2. And the Google is saying, find the max out of these, so that would be 2, and 2 is greater than 1, so this should actually work. I'm gonna have to go take my word back where we have to modify this, because we don't, but it's good to know that this is how the anti-aliasing works on Google VR, and how it's working with the distortion correction. And so previously we would have had to come in here and set something like this, because we would look at the value of this. It's an integer, so we have to assign one of these integers. So I'm going to assign the integer number 2, and so this would not a float, an integer. So this essentially is going to force the anti-aliasing to be 2. But I'm going to Control Z and just keep it as is, because if it returns the max value and is grabbing my anti-aliasing, which is 2, then that should work out. So we're going to use 2x anti-aliasing, and then we'll leave soft particles off. We'll leave these settings off. And again, if you want to look into each one individually, go here to the quality settings page on Unity. It's going to describe what all of these, each and every single one is. But they're pretty self-explanatory on this page. So we only want hard shadows. That's going to be faster for mobile VR. And we want low resolution shadows. That's faster for mobile VR. And then the rest of this stuff is pretty good, except for the VSync count. Now, we don't want to do any vertical syncing, because as it says here, VSync should be disabled. Each VR SDK has its own mechanism of synchronizing the display, and ignore VSync. So with Daydream, VSync is done. Gear VR does its own vertical sync, and we want to disable VSync for our Cardboard game as well. We only have one quality setting. We've set up the settings here. the anti-aliasing should work. And now let's go into project settings, graphics. This is where we're going to set our legacy vertex lit rendering. And if you're using Unity 5.4.2 or anything before Unity 5.5, you're going to have to find this option at your build settings under player settings, other settings, rendering path. And it's set to forward by default, and you would switch it here to legacy vertex lit. And so that's been moved in Unity 5, and that now is here in the graphics settings. And it has these different tiers, which I found pretty confusing. And so it turns out these are determined automatically by Unity, which is kind of no good. There's also a way to set it, I guess, when the scene loads, or for per scene, you can set it manually. So I'm just going to set all 3 tiers to the same exact settings, because it appears that there's not very much control over what devices these tiers, you know, cover. So I'm going to have everything set to a standard shader quality of low, and we should not be using standard shader anyways. If you look at the Oculus mobile performance, avoid use of standard shader, or definitely the specular standard shader. So we actually don't want to use the standard shader at all in mobile VR. Maybe by setting the quality to low here, like we can in Unity 5.5, maybe we would get away with it. I haven't done a lot of testing with that because this is a new option, but you know, traditionally you don't want to use standard shader. You want to use mobile diffuse and on lit shaders and vertex lit, or you know, mobile shaders. And standard shader has been a pretty expensive shader that you don't want to use on mobile VR. So I'm just going to set standard shader quality to low overall. And then the rendering path, I'm going to switch to legacy vertex lit. And legacy vertex lit is going to be set for all 3 tiers. So everything is set up the same, and I'm not using defaults on any of that. Now, here you could change the shader. We're just going to use the built-in because these shaders aren't going to be used anyways. And then there's always included shaders. If we're not going to use these, we could come in here and change these out for ones that we actually are using, or delete them completely. I'm just going to leave this to default for now until we're, you know, towards the end of the game and we really know, hey, these are the 10 shaders that the game uses, and so let's drop these into always included shaders. Shader stripping and then shader preloading, again, we can get into more of that later on. We don't even know what we're doing with our shaders yet. So we've covered everything that we wanted to on day 2, and that is, again, the build settings, the player settings here. We've got all of that set up. We've also gone into the project settings, quality, and graphics, and we've got these configured for our Android project. So now we're ready to do another build and run. I have my device, my S6 over here is plugged in and ready to go. So we'll just call this VR Tutorial Game 01.apk, and then build it and run it to the device. And then we just want to take a look and make sure everything's working. Okay, so here it is up and running, and it's definitely running at a solid 60 frames a second. And so I don't know if it actually works. I have to put it into a cardboard viewer to check it out. There we go. So everything looks amazing. And it's running at a solid 60 FPS. Okay, so we're ready to move on to day 3 and get into actually making a game. All right, you guys, thanks for watching. See you in the next video.